Good afternoon, everybody. Welcome to this session on the machine learning. So, in this session, we'll see certain aspects of hardware and IoT security, and what are the roles of machine learning in this domain of hardware and IoT security. It is how machine learning assists in imparting security to hardware systems and to the IoT system architecture as a whole. So, to start with, here is the outline of the talk. First, we'll go through the introduction. That will present the motivation that why security is indeed required for hardware. Okay, so and then we will move towards hardware for security. Okay, what are the roles and the challenges of machine learning for this domain? And then we'll move to security of hardware. That is how do we impart security to the hardware. So the first aspect is for hardware. How can we implement hardware to impart security features to the overall system, and then we come to the security of the hardware itself. Okay, and the role and the challenges of machine learning towards security of hardware, and then we'll take a look at the IoT system architecture. So it will be an overview of the IoT system architecture, and then this system architecture has got different components or different layers to it. That is the perceptron layer, or the physical layer. Then you have the network layer, the transport layer, and then you have the application layer. And each of these layers have their own security vulnerabilities. Okay, so we'll take a look at how different machine learning algorithms impart security to all these layers. And then to conclude the talk, we'll come across different issues. And is often treated as an abstract layer running instructions that are passed from the software layer that typically resides above the hardware layer. Therefore, hardware-related security research is often referred to as hardware implementations of cryptographic algorithms, where hardware is used to improve the calculation performance and the efficiency of cryptographic applications. Furthermore, hardware copyright protections are also categorized as hardware-related security research, where watermarking is widely used to solve the copyright issues. However, researchers from this area, they do not consider so the IC designer can mount attacks against the IP overusing and vulnerabilities and different vulnerabilities for the IP piracy. Then you have the foundry itself. So the foundry is the one who manufactures the chips. So as far as the foundry end, as the foundry lies in a different geographical region as compared to the usually an issue of mistrust between these two components. So that's why it leads to the threat model such as the IC overproduction. That means if the foundry is asked to manufacture n number of chips, the foundry would manufacture more than n number of chips, but wherein the additional number of chips it will sell for its profit. So this is called the IC overproduction. Then you have the defective IC production. Then the out of specification IC production, that means the specifications that have been given to the foundry can deviate from the specifications to improve the overall throughput. And then of course the foundry can mount the reverse engineering attacks on the GDS2 files that are being passed on to it, so as to extract the overall functionality of the circuit. And then in the assembly line, the malicious components over there in the assembly line, they can also reverse engineer the circuit by cutting open the IC and then have the ACM imaging technique to recover the circuit functionality. Okay. But due to the existence of multiple metal layers in the IC, this often becomes a very tedious task. And then at the last, you have the original equipment manufacturer who can also mount different sorts of reverse engineering attacks. So this is the entire security threat model in the VLSI supply chain. So basically, what happens is that in addition to this, in addition to securing the hardware itself, the broader system security properties can be enhanced by imparting hardware for security. For example, the use of hardware performance counters for identifying malicious behavior and physically unclonable functions, for implementing authentication, digital rights management, and other simple applications. So here we see the overall picture in entire IT supply chain. So first it starts from the microarchitecture specifications. So this is usually a trusted component because it starts from the IP owner end, and then you have the different design files. So this design files comprises of two components. First is the code, and then you have the HTL libraries. So now overall, over time and over here, that this HTL libraries, they can be imported or they can be bought from the third party components. So there is also an issue of mistrust over here. So that's why this HTL libraries is marked as a semi-trusted component. And then after the design, after it passes through the HTL phase, you come to the synthesis, and then the present out, and then the fab process. So each of these phases have their own component of mistrust because most of them there are third party IPs or the third party components that are involved, and this leads to different security implications in the entire IC supply chain. Okay, because over here you see that the IP cores, they can be bought from the third party components who may have incorporated some hardware Trojan functionalities. So detection and prevention of such security vulnerabilities is very important. And then you have the standard cells in the present also. So in each of these cases, okay, so as these components are bought from the third party companies, okay, there can be severe security implications in each of these cases. Okay, and finally, you have the fab process, okay, which are generally considered to be untrusted if they lie in a different geographical region. So basically, the embedded devices that come into the market after having been passed through such an IC supply chain, they have become a common in our world. For instance, we see that there are billions of small processors that are invisibly integrated in objects of our daily life. For instance, if you consider any product, for instance, vehicles, contactless payment and identity cards, smartphones, electronic locking systems, industrial machines, trains, traffic control, medical devices, and countless number of systems. Okay? So if there is a security vulnerabilities in HPCs. Okay, so same security vulnerabilities will seep into each of these applications that I stated over here. So basically, the infamous term that is the Internet of Things that has gained significant attention in the past years, implying that these pervasive computing devices, they communicate and form a global network. So with this trend, there grows the need for the security of the respective devices, as the threats are manifold, and in contrast to many PC-based applications, the security incidents can easily have direct influence on the physical world. For example, if you consider the vulnerability in a self-driving car, so wherein the driver is completely dependent upon the system functionality of that self-driving car. So evaluating and improving the security of such devices is a core problem of the field of hardware and the embedded system security. So over here, as AI and ML continues to mature, their impact on various domains, it continues to grow, including the Internet of Things and various cyber physical system applications. So the cybersecurity community is exploring potential uses of AI or ML in detecting bugs, modeling threats, and supporting defender decision making. So conventionally, before AI or ML coming into the picture, there have been design and analysis algorithms. Okay, so this group of algorithms, they pertain to the domain of cryptography and cryptology. So also earlier, this cryptography and cryptology, they were localized to the domain of the mathematical researchers. But since the 1980s, they have proposed systems to impart security to the general products. So first we'll see what are the different features that this cryptographic algorithms or the cryptographic functions impart. So first is the confidentiality. So what does confidentiality mean? So the synonym, another way means you can take confidentiality is the privacy. That is, if there is a user A and there is a user B, and user A wants to communicate a message to the user B, okay, user A wants to ensure that the message that he is sending, it should be confidential, or that is, any eavesdropper who is snooping on the communication line, the message should be unintelligible to him. Okay. So it is passed through a function that is called the encryption function that imparts confidentiality to the message. The second feature that usual cryptographic algorithms impart is the integrity or the data integrity. So what does data integrity mean? It implies that a message that is generated by user A, that message should not be tampered by any eavesdropper. Okay, so that means that there should be a cryptographic function that imparts this data integrity. And then you have the availability. What does availability mean? Availability means that any authorized user in the system, if is accessing a data on, say, a particular system, say a server, that data should be available to that authorized user 24/7. Okay, there should be a no point of time wherein that authorized user does not have access to that data. So the cryptographic system should ensure the availability of data to the authorized users. Then you have the authentication. That means if a user A is sending a data to user B, he needs to provide a proof that he is the genuine user who is generating that data. That means there should not be another user, say user C, okay, who can generate data on behalf of user A. That means spoofing. That means spoofing the user A. Okay, so that means user A should always authenticate himself that yes, he is the original producer of the data. So this is called the authentication. So there are many cryptographic functions which impart this authentication functionalities. And then you have the non-repudiation. So non-repudiation is the final, but it is also an important aspect. So what does non-repudiation mean? For instance, in this case, for instance, if user A is sending an amount of say 500 rupees to the user B, at a later point of time, user A should not be able to claim that he has not sent a 500 rupees note. He has sent a 1000 rupees amount. Okay, so there should be cryptographic functions that should enable this non-repudiation. That means the user A should not be able to claim at a later point of time that he has sent a higher amount of money. Okay, so basically many present-day applications where cryptographic functions have been incorporated. For instance, in the present day, cryptographic functions are used to perform computations on encrypted data in the cloud. They are also used in the domain of the post-quantum cryptography. But when we come to any product in the user world, okay, where we see that cryptography alone cannot solve all security issues, because there are numerous security issues when you consider an embedded system, okay, or any hardware system. So besides cryptography, you need some additional functionalities as well to impart security functionalities to such systems. So as AI and ML, so in this context, artificial intelligence or machine learning, it continues to mature, and it tries to fill up that gap to impart the security functionalities. So as AI and ML continues to mature, their impact on various domains that continues to grow, including the Internet of Things and cyber physical system applications. So the cybersecurity community is gradually exploring the potential uses of artificial intelligence or machine learning in detecting bugs, modeling threats, and supported different decision making. So most of the present research are based on the intersection between the AI or ML and the hardware security. So this research can be defined in terms of both hardware for security as well as the security of hardware. So basically, the researchers in the present day world is to provide a perspective on potential frontiers for research at these crucial junctures of hardware for security and the security of hardware. So in this lecture, we'll present a snapshot of existing challenges in hardware security and outline different opportunities and threats that exist or that are being offered by different ML algorithms. So some avenues are well explored in the literature, for example, model building attacks on PUFs, while others, such as understanding the implications of AI or ML techniques in the IC design flow, they provide new areas for exploration. Besides, AI and ML has several challenges that need to be considered by the hardware security practitioners. So that includes the design of appropriate data representations and collecting quality training data to train those ML algorithms. So there are many ways in which AI or ML is affecting hardware security, and thus they offer new directions to explore. So basically, hardware is typically assumed to be the root of trust for computer systems, where the stability that comes from committing functionality to silicon is assumed to provide a strong foundation for comparatively vulnerable or flexible software. As such, there are numerous hardware-based approaches for enhancing security, including the security primitives, such as the physically unclonable functions, or which we can say as PUFs, and cryptographic accelerators that are included as a part of an overall security architecture. So having said this, at this point, the AI or ML, it intersects with these techniques constructively as well as destructively. So defenders can use different ML algorithms with hardware-based observations to build models of an IC operation for attack detection in terms of software, hardware, and environmental conditions. On the other hand, attackers can also use different ML algorithms to extract sensitive information from an IC and breaking the trust assumptions in the hardware security. That means attackers, whatever the general conventions are in the hardware security aspects, and attackers can use different ML algorithms to extract sensitive information or sensitive data from an IC while it is in operation when deployed in a field. So basically, when we consider machine learning algorithms as well as the hardware for behavior monitoring, so as hardware sits below the software, often with layers like such as often with layers such as the operating system or hypervisor that lies in between the software and the hardware. The researchers over the past decade, they have identified opportunities for behavior monitoring using the hardware components themselves that can identify and record events or collect sensor data. So such behavior monitoring can be transparent to software. Okay? As for example, the use of hardware performance counters shows much promise for detecting the execution of malware. That means in other words, the hardware performance counters have been used for malware detection. So there have been other recent techniques as well, which include repurposing the debug hardware, such as the embedded trace buffers. Okay. A key component of these techniques is the proper analysis and interpretation of the collected activity. For example, instruction sequences and memory access events. Okay. So there are different machine learning techniques that have proven successful in this respect, and that have given them the ability to learn characteristics of malicious user behavior. Okay, so if malicious behavior that is going on in the software or hardware system, that can be captured through these instruction sequences and these memory access events. So other security approaches use hardware as a primitive. For example, the use of physically unclonable functions or PUFs, the foundation for security protocols, and unique IC identification. So PUFs basically they rely on physical phenomena for randomness, stability, and uniqueness, such as the process variations during IC fabrication. So basically you have the PPs or the process variations that come into the picture during IC fabrication. So this physically unclonable functions, they pick up these random variations that is during this process to impart different security functionalities. So in the domain of modeling attacks, where adversaries collect the different challenge response pairs, the intent to create a surrogate model of the PUF. Okay, so that is done in the modeling attacks of the PUF. In a similar fashion, researchers have used different ML algorithms to attack the cryptographic accelerators. So cryptographic accelerators, they perform computations to speed up the encryption and the decryption operations. While they do so while these accelerators they perform these computations, the hardware during their operation, the hardware may emanate signals that are correlated with the sensitive values, such as the T. Okay, for example, power fluctuations or electromagnetic emissions. So what happens usually is that most often the power dissipation that is occurring from a cryptographic accelerator, the power dissipation that becomes a function of the intermediate data on which that cryptographic operations are running on. So as the information, for instance, the Hamming weight or the Hamming distance between two successive registers, they get leaked to the power emanations. An attacker who can capture the power emanations, and if he can correlate or sync up the capture along with the data operations, then he can get significant information about the secret data, for instance, the key that are embedded within those ICs. So these are the different system threats or the machine learning algorithm based threats that have been mounted on different security functionalities. For instance, the physically unclonable functions. Okay. So now this was one aspect of hardware security. Now coming to the next aspect, that is the security of hardware. So we have seen the researchers have observed that aside from different hardware-based additions in the security architecture, we need to concern ourselves with the security of hardware itself. That means if there is a hardware that exists in a system, we should be concerned about how to impart security to that hardware itself. Okay, so in broader terms, this involves incorporating security components. Okay, so that also involves wider system-level concerns such as the security of the hardware design process and the supply chain as well. So hardware security research has been concerned with the supply chain risk where globally distributed and untrusted parties have access to the designs at various levels of maturity. So thus placing the hardware at risk of reverse engineering. So besides reverse engineering, there have been other threats such as I mentioned, IP piracy and malicious manipulation. Okay, so the recent work has shown that design tools themselves, they should be considered as a potential attack vector in the design flow. So, so as we will see, different ML algorithms can be used to aid designers throughout the design flow for the targeted security-centric application of hardware Trojan detection. So more broadly throughout the entire hardware design flow. So out of the several mature areas in the hardware security, okay, one important domain is that of the hardware Trojans. Okay, so hardware Trojans. So in addition to hardware Trojans, what is a hardware Trojan? So these are maliciously inserted functionality that are triggered during the runtime. So attackers can insert these hardware Trojans at various stages of the design flow, and they typically represent very small changes. Okay, so these hardware Trojans, they represent very small changes to the area, timing delay, and other design characteristics of that IC. So despite their stealthy nature, several AI or ML-based approaches have shown good success at hardware Trojan detection in the gate-level netlist. Okay, so there have been numerous research work or papers that have come up over the past decade in this domain. So typically, these approaches involve training and evaluation of machine learning models using the benchmarks that are sourced from the trusted community. So applying the machine learning techniques, successfully is not a trivial pursuit. However, as defenders must firstly identify an appropriate input representation for a design. Unlike the images, which are easily presented as multidimensional matrices, appropriate circuit representations are more challenging to produce to address this problem. As emerging development in the literature is the use of ML techniques in the hardware design. For example, researchers have applied different deep learning techniques at various design abstractions and design stages, including the system level prediction of the hardware overhead, logic optimization, routing, and test point insertions. That means identifying which are the identifying different algorithms for logic optimization or routing or test point insertion. Okay, so the present researchers, they have applied different deep learning techniques for such algorithms as well. So these efforts, they represent new approaches for handling scalability challenges and improve the design turnaround time. So however, while all these techniques, they claim state-of-the-art performance, the implications for hardware security in the context of untrusted supply chains and malicious insider threats. So the implications, they remain ripe for exploration. That means there can be wide range of threats towards such untrusted supply chains. So while defenders can use the machine learning algorithms to detect security issues, okay, recent work has shown that adversaries can also use machine learning algorithms in the design flow to mount attacks. Okay, so in literature there have been different works. For instance, an adversary can subvert a deep learning based lithographic hotspot detection by means of generating semantically meaningful adversarial input perturbations, where attackers insert different features to trick the hotspot detector into making bad predictions. So this points to a larger concern for the ML robustness. So that means the ML algorithms, they should be robust, at least in terms of going role in the hardware design. Okay, that means the ML algorithms, the systems should be built in such a way that ML algorithms, hardware systems. So more recently, some authors have demonstrated the potential for training data poisoning attacks that introduce backdoors into the deep learning based hotspot detectors. So during the design phase, so what happens over here is that during the design phase, a malicious insider can coerce the hotspot detector into turning a blind eye to a hotspot containing clip. Okay, despite its high accuracy under the benign setting. That means there can be certain instances wherein the hotspot detector can be turned blind by a deep learning algorithm. Okay, and this instances of time they often go unnoticed. So for completeness, it is also worth considering the intersection of hardware security and the hardware for machine learning algorithms as well. So particularly as the machine learning hardware make their way into the cloud-based IoT and CPS application domains. So there have been various AI or ML techniques that are susceptible to adversarial settings as well. So when realized as hardware, such robust weakness can translate into the new attack. Okay. So basically, when realized as hardware, these robust weaknesses can translate into new attack vectors such as the memory-based hardware trojans, fault attacks, cloud-centered interference, okay, and so on and so forth. So as AI and ML evolves and becomes more prevalent in different domains, okay, new requirements for hardware security have also emerged over the past few years. Okay. So basically, when we see the present day electronic market, so today there have been millions of embedded devices that are used in safety and security critical applications such as the industrial control systems, modern vehicles, and the critical infrastructure. For instance, over here in this picture, we see that this is an instance of a smart car factory wherein there can be parallel assembly lines, okay, for each of the components of the car. Okay, and these parallel assembly lines they are managed by an R&D or the management system. Okay, so they are subjected to the process control, monitoring, analysis, and the optimization of the entire flow of this assembly line. Okay, and then you have different cloud services, okay, that provide information to the customer regarding the product configuration, product tracking, okay, and then if the car needs a repair, okay, this cloud services they also provide the repair plans and they, and they also give the different spare part information that would be required in the repair shop. So here you see there are multiple components involved. There can be multiple suppliers. There can be different people who are involved in the production line in the smart car factory. And at each of these stages, there can be different security vulnerabilities. Okay, that this security vulnerabilities can be there during the cloud services part. It can be there during the information transfer from the R&D or the management team to the assembly line as well. Okay. So in the past few decades, classical production engineering, automation, and intelligent computation systems they have been merged into the industrial Internet of Things. So the number of computation components that are integrated into the industrial control systems, production systems, and factories they are steadily increasing over the past few years. So again, we have seen that the programmable logic controllers they are being replaced by more advanced cyber physical systems along this production line. These cyber physical systems they are really programmable. They comprise really programmable embedded devices that control different physical processes. So these CPS or the cyber physical systems they typically communicate over close industrial communication networks, but they're also often connected to the internet. So with the integration of classical computing into the production system, this emerging megatrends such as mobile computing, cloud computing, and big data are also becoming important drivers of innovation in the industry. So basically, cloud-based services are used to monitor and optimize these complex supply chains. Okay, so they have been at the center of different attacks that have been mounted on them. So big data algorithms in this respect, there have been numerous big data algorithms that predict machine failures, which reduces the downtimes and maintenance costs. Okay, so interconnected production systems, they enable tight integration and optimization of production, okay, and business process, as well as outsourcing application, outsourcing of production steps to different locations, companies as well as the freelancers. So in the near future, different cloud-based services will also allow considering more customer requirements in the production process and planning. Okay, so devices in the Internet of Things, they process and exchange vast amounts of security and safety critical data, as well as privacy sensitive information, and hence they become the appealing targets of various attacks. To ensure correct and safe operation of IT systems, it is very crucial to assure the integrity of the underlying devices. In particular, the code that is used to implement such devices, as well as the data which they process, okay, against the malicious modifications. So recent studies have revealed many security vulnerabilities in the embedded devices. This poses a new challenge on the design and implementation of secure embedded systems that typically must provide multiple functions, security features, and the real-time guarantees. So at a minimal cost. So an increasing number of everyday objects is equipped with electronics, which provides these objects with identification, computing, and the communication capabilities. So typical examples include basic technologies such as the RFID or the radio frequency identification or the identification and tracking of products, packets, and pallets in the supply chain scenarios. Okay, so this can range from the RFIDs to the smart devices such as the smartphones and whatever in different wearables, for instance, smartwatches. So this network of ubiquitous smart objects is known as the Internet of Things, and this enables novel applications and services, and particularly to the concept of the industrial sector. So there have been production facilities. So production facilities, they typically consist of several independently operating production systems with no or only limited communication capabilities. So an emerging trend is to integrate more sophisticated electronics into the production systems. Okay, so this involves integrating sophisticated electronics, okay, interconnecting them, and then integrating into the conventional business IT systems. So the resulting industrial IoT is the basis for a new level of organization and management of industrial value chains, okay, which enables high flexible and resource saving production. Okay. So typical cyber physical systems, they enable condition monitoring, they impart structural health monitoring, as well as they perform remote diagnosis as well. Okay, so further, the cyber physical systems are the basis of smart factories that dynamically organize and optimize production processes with regard to the resource utilization. Okay. So in smart factories, the smart products know their own identity, history, specification, documentation, and even they control their own production process. Okay, so beyond manufacturing, the smart products are the basis of novel knowledge-based services or the smart services. So over here we see that the cloud services that are being provided to the users of this smart card. Okay, so they are referred to as the smart services. So specifically, the smart products, they do not only collect the data during the production, but also when they are deployed and used by the customers. So this allows to optimize them with regard to the way they are actually used. So smart products are equipped with a digital identity, that is, they are stored in a barcode or in an RFID chip, and all the information related to the product is stored in some backend database. Okay, so in particular, So increased diversity and large number of devices in IoT systems, they require highly scalable solutions. For example, naming and addressing, data communication, knowledge management, and service provisioning. Okay. So for the most IoT devices, they have only limited resources, which demands for architectures supporting low power, low cost, and fully network integrated devices that are compatible with the standard communication techniques. Okay. So when we are talking about the IoT systems, it is very important to take a look at the IoT architecture. So basically, the IoTs, they convert. What do the IoT systems do? The IoT systems, they convert a physical object from a conventional object to a smart object by utilizing technologies such as the communication technologies, internet protocols and applications, sensor networks, and ubiquitous and pervasive computing. So the implementations of a flawless IoT system is crucial in the academic as well as the industrial perspective. So why it is crucial? It's crucial due to the wide range of applications that can enable the execution of a smart city concepts through billions of smart connected devices or connected smart devices. So the IoT model can be defined as the interconnection of massive heterogeneous devices and systems in diverse communication patterns, such as thing to thing or human to human or human to thing. So the IoT architecture, first, it comprises of different physical objects. So these physical objects, they are integrated into the communication network, and they are supported by computational equipment with the aim of delivering smart services to the users. So the IoT architecture, it generally has 4 layers. First is the application layer, then you have the transport, the network layer, and then you have the perception layer. So this architecture can be further taxonomized for simplicity and improved analysis, as shown in this slide. So the first layer comprises of the physical objects. So what does this layer of physical objects comprise? So the physical object level, it involves the IoT physical sensors. So the main functionality of the physical objects is to sense, collect, and possibly process the information. So this level adopts sensors and actuators such as the temperature sensors, the humidity sensors, motion sensors, acceleration sensors, and to implement their diverse sensing functionalities. Okay, so IoT sensors are resource constrained devices. So they are typically resource constrained devices because they have very limited battery capacity and they have very restricted computation capability as well. So a large part of the big data of IoT, it is generated at this level. So the increase in the IoT devices and the extensive increment in the data volume, it indicates a positive correlation between the growth of the big data and that of the IoT devices. So effective analysis of the big data of IoT can result in improved decision making for a highly secured IoT implementation. One of the promising applications of machine learning methods is the perception layer authentication. Okay? So traditional physical layer authentication techniques apply assumption checks and relate the randomness and exclusiveness of the radio channel between two persons, say Alice and Bob, to detect if the existence of a spoofing attacker. So an eavesdropper, that spoofing attacker can be an eavesdropper in that respective wireless network. So nonetheless, such an approach is not always practical, specifically in the dynamic network. So what happens in a dynamic network is that the users log in and they log off at different time instances. Okay. So this was about the physical objects. Then comes the connectivity layer. So one of the main objectives of the IoT platform is to connect heterogeneous sensors. That means the sensors which perform different kinds of functionalities or they exhibit different functionalities. So one of the main objectives of the IoT platform is to connect heterogeneous sensors cooperatively, and subsequently provide smart services. So the sensors implemented in the IoT platform are resource constrained because they are powered by batteries and have a limited computation and storage capability. So therefore, the IoT sensors must work with low power resources under a lossy and noisy communication environment. So the following connectivity challenges are encountered in the deployment of the IoT devices. The first is providing unique IPs to the billions of devices connected to the internet. So this challenge can be mitigated by incorporating different communication mechanisms. For instance, 6LoWPAN that uses the IPv6 protocol. The second challenge is to develop low power communication for transmitting data that are generated by the sensors. And then the third challenge is implementing effective routing protocols that consider the limited memory of the sensors and hence support the flexibility and the mobility smart objects. So the recent communication technologies that are employed in IoT are the 6LoWPAN, Bluetooth, IEEE 802.15.4, Wi-Fi, ultra wide bandwidth, the RFID, and the near field communication system. The next layer is the middleware. So a middleware aims to effectively represent the complexities of a system or a hardware. So thus allowing the developers to focus only on this issue to be solved without interruption at the system or the hardware level. So these complexities are commonly related to the communication and the computational issues. So a middleware. So what does a middleware do? A middleware it offers a software level application to the operating system and the network communication level. So it enables cooperative processing between the operating system as well as the network communication applications. From the computational perspective, a middleware offers a level between the application and the system software. So the main function of a middleware can be summarized as below. So it enables cooperation between heterogeneous IoT objects so that the diverse categories of IoTs can interact with one another effortlessly through the middleware assistance. So one of the key roles of the middleware is to provide interoperability between the IoT devices. The second functionality is that a middleware must provide scalability amongst several devices that are likely to interact in the IoT realm. The future growth of the IoT devices, they should be handled by the middleware by providing vital modifications when an organization scales up. So the third function is the device discovery. Okay, so the third function, it comprises of the device discovery as well as the context awareness. Okay, and this should be provided by a middleware to support the object awareness of all other surrounding IoT objects. So a middleware should provide context-aware computing to understand the sensor data. So the last function is to provide security and privacy to the IoT devices because the data collected by the IoT devices, they are generally related to the humans or an industry. So the security and privacy concerns must be addressed in such a circumstance. The next layer is the big data analytics. So the huge amounts of data that are produced or captured by IoT are extremely valuable. The machine learning towards this big data analytics, machine learning can play an analytical role in building intelligent IoT systems, okay, to deliver smart services in the IoT area. So the big data are created by several physical objects that are used in the various IoT applications. So, however, the physical devices that produce volumes of data that should be analyzed in the real time to acquire useful knowledge. So to obtain insights from this data, researchers have discussed different methods of integrating big data analytical methods with the IoT design. So unlike traditional analytical methods, machine learning and deep learning algorithms can effectively derive unobserved insights from the big data and convert that big data into the useful data with minimal human assistance. So these analytical methods can be characterized into descriptive, predictive, and perspective analytics. So the descriptive analytics is used to analyze data to describe current or past events. Predictive analytics is used to analyze data to predict the future based on the patterns that occurred in the present events. And then you have the prescriptive analytics. The prescriptive analytics is used for analyzing data to make decisions by examining various real scenarios and providing a set of recommendations to the decision maker. So the big data related to the behavior of the IoT systems, they are vital in building machine learning or the deep learning algorithms to secure IoT systems. And then finally, you have different applications such as that sit on the top of this. Okay, so these typical applications include the smart healthcare, smart transportation, smart governance, and smart grid, as well as the smart homes as well. So basically, what is the smart healthcare? So IoT devices. So basically, IoT devices have become popular in the health applications over the recent years. The IoT system is definitely becoming a key instrument in the healthcare. So wherein the IoT devices are used in the healthcare sectors to closely observe and record patient conditions and send warnings to the concerned healthcare system in the critical circumstances. So that is called the Internet of Medical Things. And then you have the smart transportation, which comprise of smart or intelligent transportation systems. So they have become attainable with the help of the IoT system. So the main objective of the smart transport is to manage daily traffic in the cities intelligently by analyzing the data from well-connected sensors located in different places and implementing the different data fusion. For instance, the data coming from the CCTVs, mobile devices, GPS, accelerometers, and different gyroscope-based applications. And then you have the smart governance as well. Okay. Then you have the smart governance, the smart grids, and smart homes, which can be defined in their own way. So now proceeding from this IoT system architecture. Okay. So proceeding forward from this IoT system architecture, we take a role of machine learning algorithms in the IoT security. So here, so IoT systems are basically complex and they contain integrative arrangements. So therefore, maintaining the security requirement in a wide-scale attack surface of the IoT system is very challenging. So solutions to impart such security requirements, they must include holistic considerations to satisfy the typical security requirements. However, the IoT devices, they mostly work in an unattended environment. Unattended means there is no manual interception. Okay? And these IoT devices, they basically typically work on their own. So consequently, an intruder may physically access these devices. So these IoT devices are connected normally over wireless access networks, or wireless networks, where an intruder may access private information from a communication channel by eavesdropping. So IoT devices cannot support complex security structures owing to their limited computation as well as the power resources. So critical consequence of the extensive application of IoT is that the IoT deployment, it becomes an interconnected task. For example, IoT systems should simultaneously consider energy efficiency. They should simultaneously consider security, energy efficiency, IoT data analytics methods, and interoperability with the software applications during the deployment stage. Okay, so this integration, it provides a new opportunity for the researchers and the interdisciplinary fields to investigate present challenges in the IoT systems from the different perspectives. However, this integration also introduces new security challenges. Okay, so whenever you are integrating multiple features, okay, so this leads to new security challenges due to the distributed nature of the IoT devices, which provide a large and vulnerable surface. So this characteristic of IoT devices, they present many security issues. So moreover, the IoT platform, it generates a large volume of valuable data. Okay, and this valuable data is related to the users. Okay, so having access to this valuable data, it gives you information about the different characteristics of the respective users in the system. So if this data are not transmitted and they are analyzed securely, then a critical privacy breach may occur in the entire system. So analyzing security protection mechanisms, for example, encryption, authentication, access control, network security, and application security is very critical and is challenging. Okay? And often at times it becomes inadequate for large systems with several connected devices, with each part of the system having inherent vulnerabilities. Okay, so it is terribly hard to impart all these security protection mechanisms such as the encryption, authentication, and access control, and so on and so forth. For example, a typical example is the Mirai botnet. Okay? So Mirai is an exceptional type of botnet that has recently caused large-scale distributed denial of service attacks, or the DDoS attacks, by exploiting a wide chain of IoT devices in the system. So existing security mechanisms, they should be enhanced to fit the IoT ecosystem. However, implementation of security mechanisms against the specified security threat is quickly conquered by new types of attacks created by the attackers to circumvent existing solutions. For example, amplified DDoS attacks utilize spoofed. So recently there have been amplified DDoS attacks that utilize spoofed source IP addresses. That means there are existing source IP addresses that are copied to the newer systems, or that is called the spoofing attack. Okay. So when you spoof the source IP address, okay, the attack location that itself becomes untraceable by the defenders. Means for example, that means what? That means if a defender, it sees there are multiple systems, computer systems that have the same set of source IP addresses. Okay, then it becomes hard for him to detect which is the actual system with the original source IP address. Okay, so these types of distributed denial of service attacks, they are very hard to prevent or to monitor. So consequently, the attacks that are more complex and more destructive than Mirai, that can be expected because of the vulnerabilities of the IoT systems. Moreover, understanding which methods are suitable for protecting IoT systems is a challenge because of the extensive variety of the IoT applications as well as the scenarios. As shown in this figure in this slide, okay, so this depicts the capability to monitor the IoT devices intelligently. Okay, and this also provides a solution to the new or the zero-day attack. Okay, so what is meant by a zero-day attack? So the name zero-day is coined considering the negligible time available in mitigating this threat. That means whenever this threats or whenever these attacks are mounted, okay, the designers of the system, they have absolutely no time to counteract them. Okay, so this picture it provides a protection mechanism that can be imparted to these IoT systems against a wide range of threats. Okay, so in zero-day attacks, the number of days for which an anomaly has been known that directly affects the countermeasures and also the probability of the remaining affected devices. Okay, so the effect of a zero-day vulnerability, it also depends on the mode of the detection. So the vulnerability cycle for a zero-day attack, they may vary from scenario or they may vary from one scenario to another scenario. In some cases, after identification of a bug, the hackers they operate covertly, leading to the full zero-day attack. Which in some cases, whereas in some other cases, the hackers may come forward and make the threat public. Okay, so whenever such attacks are mounted, okay, so these attacks can be covered, as well as these attacks can be made public whenever they are mounted. So thus it can be analyzed that a zero-day attack is not only because of the covert behavior of the attacker, but also because of the delays in updating the security patches once these are available in the public domain. So this is often explained in terms of the window of vulnerability. Okay, so the window of vulnerability is basically the time gap in which the number of vulnerable systems remaining is negligible. So machine learning and deep learning methods over here, so these become powerful methods of data exploration to learn about the normal as well as the abnormal behavior according to how IoT components and devices interact with one another. Okay, so whenever the IoT components and the devices they interact with one another, the corresponding set of the ML or the DL algorithms, they can keep a track or they can monitor on the communication processes or the protocols. So the input data of each part of the IoT system that can be collected and investigated to determine the normal patterns of interaction. So thereby identifying malicious behavior at the early stages. So moreover, machine learning or the deep learning methods could be important in predicting new attacks as well, which are often the mutations of the previous attacks. Okay, because they can intelligently predict future unknown attacks by learning from the existing samples. Okay, as the machine learning algorithms, they learn from the past events, okay, and then apply the corresponding consequences to predict the future events as well. Okay, so that's why the machine learning algorithms can be used to predict newer attacks given a certain set of communication protocols that are involved between between multiple IoT devices. So consequently, the IoT systems must have a transition from merely facilitating security communications among the devices to the security-based intelligence that is being enabled by different machine learning methods for effective and secure systems. So now we come to the various variants of IoT security threats. So various IoT applications they have different kinds. So these applications are based on different types of industry standards and specifications. Okay, that are yet to be unified into the IoT security standards. Okay, so various organizations such as the IEEE and ETSI they attempt to create IoT standards for security. The development of security standards in IoT has been reported. Current IoT-based frameworks are mostly standalone in small networks, whereas relatively few frameworks exist for the large-scale networks. As the development of IoT reach maturity, small networks they usually converge to form a large network. So a large IoT network it requires complex measures for security. But solving those security challenges will be crucial towards sustainable IoT development. As IoT structure is broadly categorized into application into the layers that I mentioned, for instance, application, transport, network, and then you have the perception layer. So each of these layers have their own corresponding attack surfaces. So a few IoT solutions also utilize different support technologies for networks, such as network processing, third-party middleware, and distributed technology as a processing layer. So these these layers of IoT structure they were also explained in an analysis of potential threats and requirements to secure IoT architecture. So each IoT layer, okay, is vulnerable to security loopholes and their activities. So these activities can be active or passive, and they can start from deformed systems or internal networks, okay, which you can refer to as an insider attack as well. So an active attack, it disturbs the operation of the presently running services, whereas a passive attack, it enumerates IoT network information without distributing the live service. So all layers of IoT devices and services, they are vulnerable to DOS or the denial of service attacks. As a result, the device and the network resources, they become unresponsive and they provide degraded customer service. So the customer service that they provide, that often degrades. So in essence, the IoT employs a transformative approach to provide consumers with numerous applications and services. So the pervasive deployment of a large number of devices also increases the attack surface. So on the other hand, the fact that IoT devices are resource constrained, therefore it is also not possible to use sophisticated security mechanisms against different notorious attacks. Furthermore, it is worth mentioning that the original internet was not designed for the IoT. So therefore, it is imperative to provide IoT security on top of the existing security mechanisms of the internet and the underlying technologies. To this end, IoT uses, as we mentioned, that IoT uses different communication technologies. Okay, for instance, IPv6, ZigBee, 6LoWPAN, and so on and so forth. Okay, so this aforementioned, communication technologies have their own shortcomings and they have the limitations from the security standpoint as well. And these limitations, they are inherited in the IoT domain as well. Okay. So in addition to these issues, the underlying TCP/IP based communication infrastructure is also prone to challenges such as the scalability, complexity, addressing, configuration, and insufficient resource utilization. Okay. So when we talk about the IoT attack services, so there can be different types of potential attacks. For instance, if we consider the physical device services, there can be a wide range of physical attacks. There can be node capture attacks as well as the user tracking. Okay, so that means if any of the sensor nodes they are captured by the adversary, so in that case the adversary can use it for user tracking. Okay. Then the potential attacks on the network services, they comprise different wireless based attacks, for instance jamming, denial of service attacks, man in the middle attacks, wormhole attacks, sinkhole, and then you have the eavesdropping attacks as well. In addition to this, you have the routing attacks, the attacks on the network ports, internet attacks, for instance viruses, intrusion and hacking, and the distributed denial of services. Okay, then you have the replay attacks as well as the identity theft. Okay, so in identity theft, this system or a computer system, it loses its own identity. That means it loses its user ID and corresponding password. Okay, so to log into that system. Then the potential attacks on the cloud services, they comprise different types of malicious attacks, SQL injection flaws, cross-site request forgery, that is CSRF, attacks on the data integrity, attacks on the virtualization. Okay, whenever an operating system, whenever there is a virtual operating system, okay, it has its own set of vulnerabilities and its own attacks. Then you have the privacy breaching attacks, the insider attacks, and then you have the flooding attacks as well. Coming to the application interface, you have different types of potential attacks. For instance, malware, spyware, viruses, okay, and then you have the blowjacking as well. So now in this in this slide we discuss the different various machine learning algorithms and their applicability in the IoT applications. So the machine learning algorithms can be classified into typically 4 categories. First is the supervised machine learning, the unsupervised, semi-supervised, and then you have the reinforcement learning algorithms. So the supervised learning algorithm is performed when specific targets are defined to reach from certain set of inputs. For this type of learning, the data is labeled, followed by the data is first labeled, followed by training with the labeled data. Okay. And this labeled data, it comprises of inputs and the respective desired outputs. So it tries to identify automatic rules. So in supervised learning, it tries to identify automatically the rules from the available data sets and then define various classes and finally predict the belonging of the elements to a different class, to a given class. That means it is kind of a classification type of an algorithm. So a supervised learning is classified as classification as well as the regression learning. So in classification learning, what happens is that the classification learning, the ML algorithm, algorithm is basically is a supervised ML algorithm where the output is a fixed discrete value or a category. Okay. A fixed discrete value means it can be a true or false type or yes and no type. Okay. So different types of classification learning algorithms that include support vector machines, the Bayesian theorem, the k-nearest neighbor, the random forest, and the association rule. So the support vector machine algorithm, that is the SVM algorithm, they are used to analyze the data that use regression and the classification analysis. So the SVM, it creates a plane called the hyperplane between two classes. Okay? So it is a classification algorithm. That means it needs to identify the classes to which a particular data set can belong to. Okay, so it creates a hyperplane named as the so it creates a plane that is referred to as the hyperplane between two respective classes. So the goal of the hyperplane is to maximize the distance from each class, which distinguishes each class with a minimum error at a maximum margin. So if the hyperplane becomes nonlinear after the analysis, then the SVM uses the kernel function to make it linear by adding new features. Sometimes it is very hard to use the optimal kernel function in the support vector machines. Okay, so basically researchers, what they do is that they apply different types of kernel functions to create such hyperplanes. So sometimes it is very hard to use the optimal kernel function in the SVM. So however, the SVM possesses a high accuracy level, which makes it suitable for security applications in IoT, such as intrusion detection, malware detection, as well as the smart grid attacks. So we are not going into too much technical steps of each of these classification learning algorithms. Then you have the Bayesian theorem. So the Bayesian theorem is based on the probability of statistics theorem for learning the distribution, which is known as the Bayesian probability. So this kind of supervised learning method, it gets new results based on the present information using the Bayesian probability. So this is also called a naive Bayes as well. So therefore, the naive Bayes or NB, it has been widely used learning algorithm that needs the prior information in order to implement the Bayesian probability and predict probable outcomes. So this is one of the challenges that can successfully be deployed in typical IoT systems. So NB is usually used in IoTs to detect intrusion detection in the network layer and anomaly detection as well. So this NB or the naive Bayes has some advantages such as simple to understand. They require less data for classifications, and they are often easy to implement. Okay, so they are also applicable for multi-stage classification, as well as this naive Bayes. It also depends on features, interactions between the features, and prior information which might resist getting accurate outcome. Then after the Bayesian theorem, you have the k-nearest neighbor. So k-nearest neighbor or the KNN, it refers to a statistical non-parametric method in the supervised learning, okay, which usually uses the Euclidean distance method. So the Euclidean distance in the KNN, it determines the average value of an unknown node, which is k-nearest neighbors. For instance, if any node is lost in the IoT system, then it can be anticipated from the nearest neighbor's average value. So the value is not accurate, but it helps to identify the possible missing node. That means to identify which node is missing. So the KNN method is used in intrusion detection, malware detection, and anomaly detection in typical IoT systems. So this algorithm is simple, cheap, and easy to apply. In contrast, it is a time-consuming process to identify the missing nodes, which are challenging in terms of accuracy. That means the nodes which need actual highly accurate information. It is very challenging to identify such missing nodes. Then you have the random forest or the RF method. So the RF or the random forest method, it is a special machine learning method which uses a couple of decision trees, okay, in order to create an algorithm to get an accurate and strong estimation model for the outcomes, for generating the outcomes. So these several trees are randomly developed and trained for a specific action that becomes the ultimate outcome from the model. So although RF uses the decision trees, the learning algorithm is different because the random forest considers the average of the output and requires lesser number of the inputs. So the random forest is typically used in the distributed denial of service attack, DDoS attack detection, anomaly detection, and unauthorized IoT services and unauthorized IoT devices identification in the network surface attacks. Okay, so there exists literature that shows that the random forest it gives better result in real-time application. It needs higher amount of training data sets to construct decision trees that identify certain unauthorized intrusions as well. Okay, so the next is the association rule or the AR. So after the random forest, there is one more rule called the association rule or the AR method. So the AR method it is another kind of supervised machine learning technique which is used to determine the unknown variable depending on the mutual relationship between them in a given data set. So the AR method was successfully used in the intrusion detection in case of a fuzzy AR system. Okay. But it is not commonly used in IoT as it has a high time complexity and it gives results on assumptions that may not provide an accurate outcome. Okay. So the association rule they are not used typically in context of the IoT system. In addition to the classification learning, the next class is the state of the regression learning. So the regression learning it refers to the cases where the output of the learning is a real number or a continuous value depending upon the way the input variables depending on the way the inputs are being given to the system. So different regression learnings comprise the decision tree, the neural network, as well as the ensemble learning or the EL. So first is the decision tree. So decision tree or DT, it is a natural supervised learning method which is like a tree that has its own branches and leaves. So DT has different branches as the edges and leaves as the nodes. So the decision trees they are used to sort out the given samples based on the featured values. So the DTs in ML is mainly categorized as classification as well as the regression. So the decision trees they have advantages over other machine learning techniques like simple construction. Okay, so the typical advantages it comprises simple construction. They are easier to implement and they can handle large data samples as well. Okay, so in contrast, this technique has some disadvantage such as it requires as it can handle large data samples, it requires big space as well to store the corresponding data. Okay, so this makes the learning algorithm more complex if there are several decision trees that need to be considered to eliminate to eliminate a certain kinds of problems. Okay, so the decision trees are widely used as classifier in security applications such as DDoS detection as well as the intrusion detection. Then you have the neural network algorithms. So the neural network techniques, they are constructed based on the human brain structure, which uses neurons. So the neural networks are widely used ML techniques that can deal with complex and nonlinear problems. So hierarchical and interconnectedness are the two main network categories in the neural network algorithm, and they are based on different functional layers of the neuron. So the NN techniques it reduces the network response time and subsequently increases the performance of the IoT system. So however, the neural networks are computationally complex in nature and they are hard to implement in a distributed IoT system. Okay. And the last class of this regression learning algorithm it comprises the ensemble learning. So ensemble learning is a rising learning algorithm in ML where EL uses different classification techniques to get an acceptable outcome by increasing its performance. The ensemble learning it usually combines homogeneous or heterogeneous multi-classifier to get an accurate outcome. Since EL uses several learning algorithms, it is well fitted to solve many problems. However, the ensemble learning it it has a high time complexity compared to other single classifier methods, and it is commonly used for anomaly detection, malware detection, as well as the intrusion detection. After the supervised learning, you have the unsupervised learning. So in unsupervised learning, there is no output data for a given set of input variables. So most of the data, they are unlabeled, where the system tries to find out the similarities among this data set. So based on that, it classifies them into different groups as clusters. So many supervising learning techniques have been used for security of IoT devices to detect the denial of service attacks using multivariate correlation analysis and implementing privacy protection techniques by applying infinite Gaussian mixture model. So in supervised learning algorithm, it comprises of different techniques as well. For instance, first is the k-means clustering. So in k-means clustering, so this is an unsupervised learning technique that creates small groups in order to categorize the given data samples as a cluster. So this is a well-known algorithm that uses clustering methods. Okay, so there are simple groups to implement this method. Okay, so first is that they differentiate the given data set into various clusters, where each cluster has a centroid or k-centroid, where the main target is to determine the k-centroid of each cluster. Then select a node from each cluster and relate this with the nearest centroid, and keep doing this until every node is contacted. Okay. Then afterwards, a recalculation is performed based on the average value of the node from every cluster. Finally, the method reduce its prior steps. That means it reiterates its prior steps until it coincides to get the k-mean value. The k-mean learning techniques are useful especially for smart city to find suitable areas for living. So k-means algorithms are also useful in IoT systems when level data is not required due to its simplicity. However, this unsupervised learning algorithm is less effective compared to the supervised learning. Okay, so the k-means clustering method is usually used in anomaly detection as well as another kind of detection that another kind of attack detection, that is the cyber attack detection. And then the last class is that of the reinforcement learning. So reinforcement learning, it allows the machine to learn from the interactions with its own environment by performing actions to maximize the total feedback. The feedback might be a reward that depends on the output of the given task. So in reinforcement learning, there are no predefined actions for any particular task, while the machine uses the trial and the error methods. So learning from the surrounding environment is one of the first learning methods that the humans experience. So the humans naturally start learning by interacting with their environment. So the reinforcement learning is typically inspired by different psychological as well as neuroscientific perspectives on the animal behavior and of the mechanisms by which agents can enhance the control of the environment. So this reinforcement learning involves making an agent learn how to map situations to actions. Okay, by presenting different kinds of situations to an agent, okay, the agent tries to learn what appropriate actions should be taken when such situations arise, okay, to achieve the highest rewards. If it is able to take an appropriate action, then that agent is given a high reward. So the agent does not have previous knowledge of which actions to implement, but it has to learn which actions produce the most rewards by attempting them through the trial and error. The features of trial and error are the main and the unique features of the reinforcement learning. Thus, the agent continues to learn from the experience to increase its rewards. So the RL has been implemented to solve several IoT and IoT security issues. So studies in the literature, it proposed an anti-jamming scheme that is based on the reinforcement learning for wideband autonomous cognitive radios, that is WACRs. The information about the sweeping camera signal and unintentional interference was used to distinguish it from other WACRs. So RLs or the reinforcement learning algorithms was used with this information to learn a subband selection policy accurately to evade the jammer signal and interference from other WACRs. Similarly, in another method, an RL algorithm based new learning was trained effectively avoid the jamming attacks that sweep over a wide spectrum of hundreds of megahertz in real time. Moreover, the reinforcement learning algorithms that they are used to provide anti-jamming scheme for cognitive radios and integrate the scheme with deep convolutional neural networks to improve the efficiency of the reinforcement learning in a large number of frequency channels. A similar scheme against aggressive jamming was proposed by a set of researchers that use deep reinforcement learning, in which the jamming was considered activated in an aggressive environment. Okay, so this is how the reinforcement learning algorithms they play a role in providing secure IoT systems. Then you have the different deep learning methods for IoT security as well. So recently, the applications of deep learning for IoT systems have become an imperative research topic. The most vital advantage of deep learning over conventional ML is that it exhibits superior performance in large data sets. So several IoT systems they produce a large amount of data. Thus, the deep learning methods they are suitable for such systems. Moreover, the deep learning algorithms they can auto-generate complex representations from the data. These methods can enable the deep linking of the IoT environment. Also, deep linking method is basically a unified protocol that permits IoT-based devices and their applications to interact with one another automatically, even without human intervention. For example, the IoT devices in a smart home they can automatically interact to form a fully smart home. So the deep learning methods they provide a computational architecture that provides several processing levels to learn the data representations with several levels of abstraction. Compared with the conventional machine learning methods, the deep learning methods have considerable enhanced state-of-the-art applications. Okay, so basically, deep learning is basically, and you can consider the deep learning to be an ML subfield that utilizes several nonlinear processing layers for descriptive or generative feature abstraction and transformation for pattern analysis. So these deep learning methods are also known as the hierarchical learning methods because they can capture hierarchical representations in the deep architecture. So the working principle of deep learning is typically inspired by the working mechanisms of the human brain and the neurons for processing the signals. So the deep networks are constructed for supervised learning, unsupervised learning, and the combination of this learning type that is called the hybrid deep learning. So the supervised deep learning, or you can say, we can refer it to be as a discriminative learning. So in this, the commonly supervised deep learning approaches they comprise the convolutional neural networks or the CNNs and the recurrent neural networks or the RNNs. So the CNNs were introduced to reduce the data parameters used in a conventional ANN, that is conventional artificial neural network. The data parameters are reduced by utilizing three concepts. First is that of the sparse interaction, then you have the parameter sharing, and then the equivariant representation. The reducing the connections between the layers increases the scalability, and thus it also improves the training time complexity of a convolutional neural network. A CNN consists of two alternating types of layers. First is the convolutional layers, and then you have the pooling layers. So the convolutional layer it convolutes data parameters with the help of multiple filters or kernels of data of equal size. So the pooling layers they perform downsampling to decrease the sizes of the subsequent layers through max pooling or average pooling. So what does the max pooling do? So the max pooling it divides the input into non-overlapping clusters and selects the maximum value for each cluster in the previous layer, and whereas the average pooling it averages the values of each of the clusters in the previous layer. Okay. So another important layer of a CNN is that of an activation unit, which performs a nonlinear activation function on each element in the feature space. So this nonlinear activation function is selected as the it is referred to as the rectified linear activation function, which involves the nodes with the activation function fx, that is basically a maximum selects a maximum of 0 or x. So the main advantage of a convolutional neural network is that it is exclusively applied to the training approaches in the deep learning algorithms. So it also allows for the automatic learning of features from raw data with high performance. However, a CNN has high computational costs. As it involves so many layers, it involves a high computational cost. Thus, implementing it on a resource-constrained devices to support onboard security systems is typically challenging. Nevertheless, there have been distributed architectures. There have been numerous distributed architectures that have been proposed that can solve this issue. So, in this architecture, a light DNN or a light deep neural network is implemented, and it is trained with only a subset of important output classes on board. But the complete training of the algorithm is achieved at the cloud level or deep classification. After CNNs, you have the RNNs or the recurrent neural network. So an RNN is a vital category of the deep learning algorithms. So RNNs were proposed to handle sequential data. In several applications, forecasting the current output is based on the analysis or associations of the several previous samples. So thus the output of the neural network, it depends on the present and the past input. So in such an arrangement, a feed-forward neural network is inappropriate because the association between the input and the output layers, they are preserved with no dependency. So therefore, when the background algorithm was introduced, its most remarkable application was the training of RNNs. So for applications that consist of sequential inputs, RNNs are recommended. So an RNN or a recurrent neural network, it integrates a temporal layer to capture the sequential data and then learns multifaceted variations through the hidden units of the recurrent cell. The hidden units are then modified according to the data that is presented to that network, and these data are continually updated to reveal the present condition. That is the present conditions of the network. Mistake can be different conditions. For instance, the congestion level of the network. So the RNN, it processes the present hidden state by estimating the subsequent hidden state as an activation of the formerly hidden state. So the RNNs are used because of their capability of managing the sequential data effectively. That means it can effectively use the past data. So this capability is advantageous for various tasks such as the threat detection, in which the patterns of the threat are time dependent. That means if the present threat pattern is basically a function of the previous threat pattern, then in that case the recurrent neural networks helps in predicting such threats. So therefore, using the recurrent connections can improve the neural networks, and they can also reveal important behavior patterns. So the main behavior of the recurrent neural networks is the issue. The main drawback of the recurrent neural network is, however, the issue of vanishing or exploding gradients. So RNNs have been typically used for IoT. It is the IoT devices, they generate large amounts of sequential data from the several sources, such as the network traffic flows. So basically the network traffic flows of the past network traffic flow, and from that, if any data is generated, are be used to recover important information. So, for example, the feasibility of an RNN was studied in examining network traffic behavior to detect potential attacks, for instance, malicious behavior, and this confirmed the usefulness of the recurrent neural networks in classifying the network traffic for accurate malicious behavior detection. So thus RNNs or the recurrent neural networks, they provide a practical solution in real world scenarios. So after this RNN, we have the unsupervised deep learning approach. So in this, it comprises of common unsupervised DL approaches. it comprises the deep autoencoders, deep belief networks, and restricted Boltzmann machines, not the RBMs. So first is the autoencoders or the deep autoencoders. So a deep autoencoder is an unsupervised learning neural network that is trained to reproduce its input to its output. Okay. And AE is so an autoencoder. It has a hidden layer which defines a code used to represent the input. So an AE neural network is divided into two parts. First it comprises of an encoder function H. Okay, and then you have a decoder function which attempts to reproduce the input. So given an output, it attempts to reproduce the output. Okay, so it has first an encoder function, and then it has a decoder function that attempts to reproduce the input. So the encoder, it obtains the input and converts it into an abstraction, which is generally termed as a code. Okay, subsequently, the decoder acquires the constructed code, which was initially produced to represent the input. To rebuild the original input, okay, then the training process in the autoencoders should be accomplished with the medium reconstruction error. Okay, but the autoencoders, they cannot learn to replicate the input perfectly. So these are also restricted because they can produce an approximate copy only. Okay, so this is one of the drawbacks of this autoencoder. So the model is required to prioritize which characteristics of the input should be copied. Thus, so hence the autoencoders, they frequently learn useful characteristics of the data, and they are potentially important for feature extraction from the input data. So these AEs or the autoencoders can be successfully used to represent to learn features, and hence reduce the dimensionality with no prior data knowledge. Okay, so the AEs, so in the past decade, these autoencoders, they were used to detect the network-based malwares. The AEs were trained to learn the latent representation of a diverse feature set. Particularly, the autoencoders were trained on the feature vector that are extracted from the cyber physical systems. So the AEs exhibited better detection performance than the conventional machine learning algorithms such as the SVMs or the KNNs. Then you have the restricted Boltzmann machines. So these are deep generative models that are developed for unsupervised learning. So an RBM is a completely undetected model with no link between any two nodes in the same layer. Okay, that means the nodes in the same layer, they are independent of each other. So these RBMs, they consist of two types of layers. First is the visible, and then you have the hidden layer. A visible layer holds the known input, whereas a hidden layer consists of the multiple layers that include the latent variables. So the RBMs hierarchically understand the features from the data, and the features captured in the initial layer are used as latent variables in the subsequent layer. Okay. So basically, there have been numerous experimental results that show that the classification performance of a discriminative RBM is typically affected when the classifier which was used to test a network data set that differed from the network data set on which the classifier was trained. So the finding is further investigated and to determine how a classifier can be generalized to detect an anomaly in the network data. Okay, and that anomaly can exist in different network environments as well. So the feature representation capability of a single RBM is typically limited, but it can be substantially applied by stacking two or more RBMs to create a DBN or a deep belief network. So what is a deep belief network? So deep belief networks are basically generative methods. So a DBN consists of stacked RBMs that execute greedy pairwise trading to perform robust performance in an unsupervised environment. So in a deviant, the training is accomplished layer by layer, each of which is executed as an RPM that is trained on top of the formally trained layer. Okay, so the deviants have been successfully implemented in a malicious attack detection. There have been some research that there is research that has proposed an approach to secure mobile edge computing by applying a DL-based approach to for malicious attack detection. So that study used a DBN or the deep belief network for automatic detection, and the proposed DBN-based model showed vital improvement in the malware detection accuracy as compared to the ML-based algorithms. So this result demonstrated the superiority of the of deep learning algorithms in general and deep belief networks in particular as compared to the conventional manual feature engineering methods in the malware detection. Okay. So basically these DBNs are unsupervised learning methods that are trained with unlabeled data iteratively for significant feature extraction. So, however, even though these DBNs are use contrastive convergence to reduce the conventional times, these networks are still inapplicable on onboard devices with limited resources. Okay. And then you have the semi-supervised or the hybrid deep learning. So, in this, the typical deep learning approaches that are used are the generative adversarial networks or the GANs and ensemble of deep learning networks or EDLNs. Okay, so these are some of the typical examples. So GANs have recently emerged as promising DL frameworks. So GAN framework framework simultaneously trains two models, namely the generative as well as the discriminative models via an adversarial process. Okay. So the generative model, it learns the data distribution and generates data samples, and the discriminative model, it predicts the possibility that a sample originates from the training data set rather than the generative model. Okay, so the performances of the discriminative and the generative models are typically measured by correctly or incorrectly classified samples. Okay. Subsequently, both these models, they are updated for the next iteration. Okay, the output discriminative model, it assists the generative model to enhance the samples generated for the subsequent iterations. So GANs have recently been implemented for IoT security. Okay, for instance, for securing the cyberspace of the IoT systems, and the GAN algorithms in this, the GAN algorithms were integrated into the proposed architecture for a preliminary studies. Okay, so GANs have a potential application in IoT security because they learn different attack scenarios to generate the samples similar to a zero-day attack. Okay, and hence provide algorithms with a set of samples beyond the existing attack. So the GANs are suitable for training classifiers through a semi-supervised approach. Okay, so next is the example of DL network. So several DL algorithms can work collaboratively to perform better than independently implemented algorithms. So these EDLNs or the ensemble of DL networks, they can be accomplished by merging generative, discriminative, or the hybrid models. So these EDLNs are often used to handle complex problems with uncertainties and high dimensional features. So an EDLN, so what does an EDLN comprise? It comprises stacked individual classifiers, which can be either homogeneous, that is classifiers from the same family, or it can be heterogeneous, that is classifiers from different families. Okay, and they can be used to enhance the diversity, accuracy, performance, and the generalization as well. Okay. So these EDLNs have achieved remarkable success in many applications such as human activity recognition. Okay. Also, the EDLN application in IoT security, it needs further investigation. Okay. Particularly with the possibility of implementing light homogeneous or the heterogeneous classifiers, as it applies an ensemble of both homogeneous and heterogeneous classifiers. Okay, so it finds its use in typical IoT security systems. Okay, and the last you have the deep reinforcement learning algorithm. So in this, the reinforcement learning algorithm it incorporates different methods such as the deep Q network, okay, and they have been introduced as a strong alternative to solve the high dimensional problems and establish the scalability and uploading the efficiency in various mobile edge computing based applications. So one of the recently successful RL methods is the deep Q network. So extensions of deep Q network or DQNs have been suggested that include double Q learning. Okay, so I'm not going into the details of this deep reinforcement learning, so you can take a look at the respective literature. Okay, so after this, we take a look at different application detection, okay, application or attack detection that have been mounted with different ML algorithms. So first, with the neural networks, these neural network algorithms, they have been used for security of IoT network, the denial of service attacks, the intrusion detection or malware detection, and they have been also used to impart privacy of an IoT entity. So this IoT entity can be a cloud-based entity, or it can be a node, or it can be a sensor node as well. Also, neural networks have been used to impart security of mobile networks. Then you have the KNN algorithms that are also used for intrusion or malware detection. They have also been used for detection of anomalies, that is the anomaly detection, or the false data injection attacks. Okay. In addition, impersonation attacks and authentication of an IoT entity. So for both these purposes as well, the KNN algorithms or KNN have been used. Then you have the SVMs. So this is another typical class of supervised learning algorithms that have been used. So they are also used for intrusion or malware detection. They are used in the security of mobile networks as well. And in addition, it is used for the false data injection attacks, detection of false data injection attacks, authentication, and also detection of data tampering. Then you have the decision trees. They are used in the detection of intrusion and detecting suspicious traffic sources. Then you have the assemble learning. So they are used for intrusion or malware detection. They are also used for false data injection attacks. And in addition, they are used for source authentication as well as detecting any data tampering efforts by the eavesdropper. Then you have the K-means clustering. Okay, so in the K-means clustering, they are used for cyber detection in the industrial wireless sensor networks. They are used for private data anonymization in an IoT system, and also any attempt to tamper the communicating data between two sensor nodes or two entities in an IoT system. Then you have the naive-based algorithm or the NB algorithm that we discussed. It is used for typical intrusion detection or the anomaly detection. Okay, and it is also used in the security of an IoT entity or the traffic entity. Then the random forest. Random forest is used for typical intrusion detection or the malware detection. It is also used in detecting anomalies, different kinds of distributed denial of service or DDoS attacks, and detecting unauthorized IoT devices that exist in the IoT ecosystem. The principal component analysis technique, this is used for real-time detection systems, and it is also used for intrusion detection systems. Typical reinforcement learning algorithms, they have been used for detecting DOS attacks, or the denial of service attacks, spoofing attacks, the eavesdropping attacks, the jamming attacks, and then the malware detection attacks. I am not going into the details. You can refer to the respective literature for each of these detection mechanisms. And then you have the association rules for intrusion detection. Okay, so then we come to the last part of this lecture, that is the different issues, challenges, and the future directions that exist for ML algorithms with respect to the IoT security. So basically, we can generate a list of issues, challenges, and future directions for using the ML and DL methods to mitigate the security weaknesses in typical IoT systems. So these weaknesses can be based on the data. They can be based on the learning activities. They can be based on the IoT environments, inherent ML and DL challenges, as well as the opportunities to integrate different ML or DL with other technologies. Okay. So the first issue is the availability of the security security-related data sets. So basically, the present-day researchers, when they go for the application of machine learning algorithms, they often face they often encounter this learning algorithms. So the general purpose of learning algorithms is capturing the patterns from the available partial training data set and then constructing a model to characterize the new inputs on the basis of the learned patterns. Okay, so in this process, a question is to investigate is the volume of the training data. Okay? That means it requires a large volume of training data that is required to train the learning algorithm sufficiently. Okay? So in the context of the application of ML and DL machine learning and deep learning algorithms for IoT security, the major challenge encountered by such algorithms in general by the supervised machine learning algorithms and the supervised DL algorithms is to extract or to generate a to extract or generate a high quality training data set that contains various possible attack types. That means it requires high quality training data set that can correlate to different types of attack variants. So a high quality training data set is an essential ingredient to train the ML and the DL algorithms. And this training data set should be comprehensive and diverse. So it is a major challenge to procure such a security related data set. So this is one of the biggest challenges or the issues that are being faced by the present day machine learning algorithms. So this training data set should be comprehensive and diverse. So they should contain information that reflects nearly all of the strategies of the real world attacks, because these training data sets are the basis for obtaining the model knowledge. So this condition can directly influence the model accuracy. So given that the IoT systems generate large volumes of data, real-time data streaming or real-time data streaming quality, maintaining such a quality, it always remains a challenge. So vital future research direction is the use of crowdsourcing methods for generating such data sets related to the IoT threats and the attacks. So rich data sets that include nearly all attack patterns should be generated for training this ML and the DL algorithms. Furthermore, such data sets can be used to benchmark the accuracy of newly proposed algorithms against that of the existing methods for attack detection. So although generating collaborative IoT threat data sets which can be continuously updated with the new attacks is of great importance. It's challenging technically due to the wide diversity of the IoT devices. Furthermore, a privacy issue prevails because the data sets may contain sensitive or critical information that are not meant to be shared publicly, specifically for industrial and the medical IoT devices. The next issue or the challenge that you can refer to is the learning to secure IoT with the low quality data. So most of the proposed deep learning algorithm representations are generally for high quality data. However, IoT systems comprise heterogeneous connected devices and large scale stream. So that leads to the possibility of high noise and corrupted data that is gathered from such systems. So therefore, learning to secure IoT systems typically requires deep learning models that can handle and learn from low quality data, particularly when obtaining high quality data is practically invisible. So this is one of the major challenges. And then you have the different learning strategies for effective IoT security. First is the zero-day attacks on IoT. That is the main disadvantage, the main advantage of ML and DL methods over traditional security methods. That is such as the signature based detection method is that applicability to detect security attacks. That means there are classes of ML and DL algorithms such as the reinforcement learning algorithms, okay, that became efforts that can be trained to predict the zero-day attacks in advance, okay, so that they can be mitigated just at their onset. Okay, so detecting such malware zero-day attacks that is typically hard by using the conventional methods. Okay, so the number of emerging IoT security threats such as this zero-day attack is continuously growing at an alarming rate. For example, the Mirai botnet that I stated earlier and its various variants are becoming an alarming threat to the security of the IoT systems. So the development of the recent derivation of the Mirai botnet, okay, for instance, there have been a recent variant of the Mirai botnet that is the Satori botnet. So it proves that the other malicious IoT botnets are emerging to exploit known and zero-day vulnerabilities. So the next issue is the lifelong learning for learning the IoT threats. So one of the main characteristics of the IoT environment is dynamism. It is several new things join and numerous objects leave the system, given the numerous and the diverse IoT devices used to manage different applications and scenarios. Given the IoT's nature, normal structures and patterns of IoT systems may considerably change with time and threats and attacks that target the IoT system may likewise persistently vary with time. So therefore, distinguishing between normal and abnormal IoT system behavior cannot be always predefined. Okay, so the concept of lifelong ML is guided towards construction of a model that can repeatedly perform the retaining process for learning new emerging patterns related to such behavior. So the model should be able to continuously adapt to and learn from the new environment. So the researchers over the past decades they have reported that the further training an algorithm receives with the latest features are known DDoS attacks. The more this improves the detection probabilities for known and unknown DDoS attacks. And then the last, you have the transfer learning. So the transfer learning it refers to the idea of transferring knowledge from a domain with sufficient training data to a domain with insufficient training data. So the main purpose of transfer learning is to reduce the time and the effort required for the new learning process. The main concern in the transfer learning it deals with the part of the knowledge that can be transferred as knowledge that is common between the domains. So therefore, transferring such knowledge is useful. Meanwhile, transferring knowledge that is specific for a particular domain and does not hold any importance to other domains must be avoided. The concept of transfer learning, which consists of different elements such as devices, wireless sensor network, and cloud computing, can be useful for securing IoT systems. So the security of these systems have already been extensively studied and well established by training samples on different attacks have been generated. Okay. And in addition, there are numerous ML and DL challenges that the researchers are presently observing. First is the possible misuse of machine learning and DL algorithms by attackers for breaking the cryptographic implementation by ML methods. Okay, so there have been numerous recent advances in ML and DL algorithms that have enabled them to be used in breaking the cryptographic applications. For example, there have been studies that use machine learning algorithms to break cryptographic systems using support vector machines, and the performance of applying such support vector machines, they have been observed that they outperform the conventional template attacks that have been conventionally used to break the cryptographic system. Similarly, researchers investigated different deep learning algorithms to break cryptographic systems and reported that deep learning algorithms can break cryptographic systems as well, much more effectively or efficiently. Especially CNNs or the conventional neural network and auto-encoding algorithms, that is the AE algorithms, they perform better than the conventional ML algorithms such as the SVM and the random forest. Okay, so then you have the other class of machine learning and the deep learning challenges are the privacy of ML and DL. That means there have been recent studies that show that the ML and DL algorithms these algorithms can itself leak information about the data. So hence, the privacy preserving ML and DL algorithms are vulnerable to dominant attacks. So a study showed that distributed or even decentralized DL methods are easily broken and they are unable to maintain the training set privately. Okay, that means if a training set needs to be kept secret, okay, is applying a DL algorithm or ML algorithm, they tend to leak information about the secret data. So these are some of the typical issues and the challenges that exist with respect to the ML and DL algorithms when they are applied on the secure set of data. Okay. So these algorithms, they themselves are vulnerable to potential attacks when generating the training data. Consequently, attackers can build a deep learning system that can recognize how DL-based detection methods work and hence generate attacks that can be detected easily. So that means it becomes a cat and a mouse game between two sets of DL algorithms. Okay. So these are some of the challenges that exist in the present day ML and DL algorithms with respect to the IIT security system. So with that, I conclude my talk. Thank you.